Welcome to today's paper reading. Today's paper is titled, Generation Constraint Scaling Can Mitigate Hallucination. This paper was published on the AR14 preprint by Georgios, Kollias, and colleagues from IBM Research. The abstract addresses the significant issue of hallucinations in large language models, LLMs, which are closely linked to memory mechanisms. The authors explore a novel approach to mitigate hallucinations by incorporating explicit memory mechanisms into LLMs. They demonstrate that scaling the readout vector in a memory-augmented LLM decoder can effectively reduce hallucinations without the need for additional training. This geometry-inspired method not only outperforms existing state-of-the-art LLM editing techniques but also enhances the quality and efficiency of generating Wikipedia-like biography entries. Large language models, LLMs, demonstrate significant capabilities in tasks such as language generation and machine translation. However, these models often suffer from the issue of hallucinations, where they generate incorrect or misleading information. To address this, model editing techniques have been developed, which involve modifying the model's parameters to produce desired responses for specific queries while maintaining accuracy for other inputs. Another approach is context grounding, where the desired response is included in the prompt context. Given the psychological link between memory and hallucination, it is hypothesized that LLMs with explicit memory mechanisms could reduce hallucinations. This study investigates this hypothesis using Larimar, a recently proposed LLM decoder enhanced with an external memory system. Unlike previous practices, we examine the geometry of the memory representations and use our findings to develop a method for mitigating hallucinations. We compare Larimar's performance on a hallucination benchmark with GRACE, an existing model editing technique, to evaluate its effectiveness. Larimar is a class of large language models, LLMs, enhanced with an external episodic memory controller. The architecture of Larimar includes three main components: an encoder, an associative memory module, and a decoder. The encoder is responsible for computing latent representations of textual inputs and queries, which are then used to update the memory and query it for information. The decoder generates text output based on a prompt, with its generation process constrained by the readout from the memory. Notably, the readout vector functions as a special key-value cache within the decoder, which expands into key-value pairs for each layer through a weight matrix learned during training. This mechanism allows the decoder to adapt to various conditional inputs without the need for retraining, similar to the approach described in Optimus by Lee et al., 2020. The GRACE method is designed for editing large language models without altering their weights. This is achieved by installing a special adapter, known as the GRACE adapter, at one or more layers of the model. The GRACE adapter operates using a dynamically expanding key-value codebook. In this system, a key represents the layer's input activation, while its corresponding value is the input to the next layer. This value, when substituted, ensures the correct output for the given input-output sample pair. The values in the codebook are learned by minimizing a task-specific loss function. Experiments involving this method include evaluating its effectiveness on specific tasks, using appropriate datasets and models, with the aim of mitigating hallucination in the model's outputs. The experiments utilize the Wikibio dataset, which consists of 238 subjects with biographies generated by GPT-3 and annotated for factuality accuracy. Authors fine-tuned GPT-2XL on this dataset mixed with sentences from open web text to mitigate hallucination. Additionally, the Larimar model is employed, which combines a BERT large encoder with a GPT-2 large decoder and a memory matrix, trained on 7.6 million examples. Figure 1 illustrates the Larimar pipeline for processing pairs of prompt input sentences. The Larimar decoder explicitly handles these pairs, while the encoder implicitly converts tokens into latent vectors. The decoder generates output text based on the prompt, constrained by the readout vector obtained from querying the memory. Figure 2 illustrates the relationship between readout and generate vectors in the Larimar decoder. It highlights that the decoder arbitrarily distorts both the direction and magnitude of incoming readout vectors. Consequently, generate vectors tend to increase in magnitude and deviate over a broad range of acute angles from their decoder inputs, making it difficult to connect the two vector types. Figure 3 illustrates the significant deviation between zWrite and zReadout vectors when a random prompt is enforced as the query prompt. This deviation is characterized by a contraction in vector lengths by approximately a factor of times 10 and a wide distribution of angles ranging from 0 to 180. This phenomenon highlights the inability to connect these vectors under such conditions, which is crucial for understanding the generation constraints in Larimar. Table 1 presents the Georgios scores averaged over Wikibio entries for various scaling factors S applied to the readout vectors. The scores indicate that the maximum Georgios score of 0.72 is achieved when the scaling factor S is set to 4. This score represents a significant improvement over the baseline, demonstrating the effectiveness of scaling and optimizing generation quality. Notably, the Georgios scores begin to decrease after the scaling factor exceeds 4. Suggesting an optimal range for S between 3 and 4. Figure 4 illustrates the alignment between the write and readout vectors in Larimar when standard constraint generation is in effect. Despite a relative decrease in vector length by a factor of times 3 to times 4, the two vectors are very well aligned, with their angles being tiny fractions of 1 degree. This alignment suggests a method for mitigating hallucination by scaling up the length of the readout vector, thereby maintaining a minimal distance to the write vector and optimizing generation for reduced hallucination. Figure 5 illustrates the jacket similarity scores across various scaling factors as applied to zReadout in the Larimar model. The mean jacket similarity scores for the ideal scenario in Larimar, where zWrite equals zReadout, and for the Grace model are included as horizontal lines for comparative analysis. This visualization helps in understanding how different scaling factors impact the similarity metrics within the Larimar framework. Figure 6 illustrates the geometric alignment between input and output latent space representations in the context of different scaling factors S for zReadout. The left panel shows the mean vector distances, while the right panel displays the mean angles in degrees. The data indicates that the alignment is optimal in the vicinity of scaling factors 3 and 4, where both distances and angles are minimized. The Larimar encoder memory decoder architecture demonstrates the potential of using lightweight memory primitives to constrain generation in the decoder. This approach provides a training-free method to mitigate hallucination. Geometry-inspired operations, such as vector scaling on memory readouts, are particularly effective in models like Larimar that include an explicit memory mechanism. These operations are shown to be more effective than training-based approaches like Grace, which involves learning adapter layers parameters through training. Thank you for watching.